All right, so I'm not actually going to talk too much about Rust. I'm just going to go into I'm just going to do an introduction of why I think it would be useful for embedded programming. And I've actually just put some Haskell code here, not because I'm going to talk about Haskell at all, but my point is that I really think that programming languages, they're all good. Well, some of them better than others, but they're good. I should stay here, shouldn't I? But I really think it's about using things that are good for their use case, right? Haskell, I think personally, it's just a compiler that I'm developing for some DSP stuff. It's brilliant for writing compilers. It's really good for doing symbolic processing. Very good at doing static checking. It's not that great to run on a tiny little microcontroller with very small amounts of memory. Now, people will try, but they're research projects. The garbage collection, it's debatable whether you want to do that on those things. Oh my gosh. There we go. And so all my point is that I think there's been a lot of developments in programming languages over the last 20, 30 years, particularly driven by languages like Haskell, but also languages like JavaScript, dare I say Java, but too, probably. And actually in the last 7 or 8 years, including C++ as well, right? There's been that. C has been slowly catching up in some ways, and it doesn't need to change that much because it's very good. It does exactly what it says in the tin. But when we think about programming microcontrollers, I think that we probably could take on board some of those modern developments and apply them where appropriate. That doesn't mean once I think it's interesting and that my kids use it, MicroPython is really cool and it's great that you can run it on a BBC microbit, for example. Do I think you should do production development in it? Probably not, right? But it's a great teaching tool, so it just depends on what you're trying to achieve. Scratch, I found it quite hard to teach to my students, but it's still a good tool for what it does. Okay, so now that was just a little precursor. I'm from the University of West of England in Bristol. Oh, fuck. Is it going to miss off half my slides now? All right, let's see how it goes. It's so going to cut them off, isn't it? Anyway. All right, so I'm just going to move on. So it's an embedded world. Oh, really? It's not. I'm going to have to change the resolution. Sorry. Let's see if we can see it now. Go back to here. Present. Wow. It's mind-boggling.
Just continue your talk.
Okay. All right, I'll just continue. No, indeed. All right, so here's, I'm coming from an embedded perspective. I do a lot of stuff with the Internet of Things and physical computing, with building devices, all of these sorts of things. And what we're really seeing, I'm teaching a course on Internet of Things to my second year undergraduate students, and very few, they're all computer science students, but very few of them are that good at programming, to be frank. They're certainly not that good at C programming. A lot of them do Java in their first year. And, it's fine. If you want to, I've got nothing against it, and I'm not a huge fan of it personally, but it's fine. But they come along, and we teach an operating system course in the previous module, and in this one, we're all using C and pointers, and, they kind of bash along with it. But some of them find it quite difficult. And to be honest, a lot of it's unnecessary. I think that, but we need to program these devices at this level. It's very hard. They have to be system level languages as far as I'm concerned. And so, we care about high performance. But we do want an easy software experience. That's the thing. I've been teaching embedded programming for quite a while to students that are expecting embedded programming. They know what JTAG is and all of those sorts of things. They know what OpenOCD is. By the time they arrive at my course, it's really not that hard just to continue with that. But if you've got students who have no idea outside of Visual Studio or NetBeans, it's quite a different thing. And then, moreover, I'm starting to teach some of this stuff to schools and everything. And it can be a difficult experience. GDB is a pain in the arse, and the development tools on Linux aren't great unless you're really, really experienced with it, right? It's not a nice experience to come to it straight away. I see students go to Visual Studio, and it is a pretty nice experience, and I think it's naive to think it's not. And I want the embedded development to be similar, right, to have that kind of feel. Still, when you go to Visual Studio, you develop in C++, and I think that's great. I don't pretend that all of a sudden we're going to replace systems programming languages with these high-level languages on embedded architectures. That's not going to happen. So I want to find some sort of middle ground to make that. So we've been looking at the CORTEX-M architectures. ARM's British company, but actually, to be honest, the CORTEX-M are really quite good processors. They're very cheap, they're accessible. We mostly use ST, not for any other reason than they produce lots of chips, they're cheap, they're good. And there's a wide range of applications that you might want to do with it. For example, the M7, which is their monster processor, has everything in it. I mean, if you think back 20 years, this would be a pretty good desktop machine. And actually, we've just got the H7 from, which is an STM implementation, and it runs at 400 megahertz, which is quite impressive. It's got a kilobyte of RAM and so on and so on. It's a kind of impressive processor. You can have off-board SD RAM, all that sort of stuff. So it does do, it's a very powerful chip, okay? And that means the consequence of that is that we are starting to write software that goes way beyond what traditionally would have been found on embedded architecture. And what I mean by that is that software development is much more complex. You are writing, large programs relatively. Okay, they're not the millions of lines that you put in operating systems, but they're still reasonably large programs. And if you think back, I went to the Unix talk yesterday on the history of Unix, and they said the first version was of 2.5K, I think, lines of pure assembler code. And today it's millions or whatever. And I'm not expecting embedded to go like that, but still, it's going to grow quite rapidly. And using the techniques that we've used to program embedded architectures continually, it's going to make it very hard to sustain that. MCU, there's a whole set of range of MCUs. The STM is the ones that we use. I'm not promoting ST in any sense. I did work there for a while, and so maybe I shouldn't promote them. But they do provide a very nice, they provide a kind of very wide and varied set of architectures for depending on what you want to do, all the way down from M0s, which are, tiny little stamp-size chips running at hardly any power with nothing, don't even have systics on some of them, all the way up to these very high-end microprocessors, which, are getting close to, they're not quite application, but they don't have MMUs and stuff, but they do have hardware protection units, those sorts of things. And so it's varied. The nice thing, I think, about the ARM architectures, and again, I'm not advertising ARM in any reason, is that it kind of goes up. It's always backwards compatible, so you can take your programs, and they're fairly easy to port up the hierarchy as you feel you need new features. And so you can choose what's beneficial. If you need an FPU, you can add that. You don't get that to an M3. If you need DSP, I think you get that in M4, and so on as you go up the hierarchy. And I haven't looked at it at all, but the M33s, I think I was looking at yesterday, just on their website, now have trust zone as well, so you can start to have areas where you can embed keys and all of that sort of stuff, And so this, you can imagine, it's quite a complex software stack. And when I come back to the beginning, when I was talking about the Internet of Things, it's a software stack that has to care about security, right? It has to care about, things like denial of service. Then these things are going to store your keys on them. Potentially, you're going to be buying bitcoins with them. I don't know, whatever. And they need to be secure. And to be honest, we haven't done a great job of that with some of the other OSs and so forth and things. I mean, we're doing much better now, but I think that we do need to be aware of that. And obviously, ARM are thinking about that by adding trust zone, which is their secure area where you can have secure bits of memory, which only certain bits of code can access, and those sorts of things. They're seeing that as a potential market as we go forward. Okay, I'm sure you've all seen, again, I personally think it's an awful thing, but the Amazon Dash, where you have this little button and then you press something and it orders your washing liquid, really. It's hard to go to the computer. Anyway, whatever. But, every application, anything to make money, I suppose. But, these things are there. That works by a little optical thing. You take it to your phone and it quickly enables you. You put in your password and go onto Amazon. It's all linked up. So all this onboarding process, you're sharing all your keys and things. I don't know, there was an example this guy from Dyson showed me, where he took this carp, he bought it in a shop called Maplins in the UK, which is basically a bit like, Radio Shack or whatever, but not as good. And so it's carp, the Internet of Things, it measured the temperature, I think, on the humidity of the room. And he went and showed it, it set it all up in this example, put it online, and then got a little text app and started to connect to it, and because it just sets up a hotspot, and you could just see your password going by in text, it was incredible, They'd spent 3 years working out how you could do this 256-bit encryption to connect their Hoover. It was like a little, these automated Hoovers around the house. He showed the forums. 99% of the complaints was it was too hard to get online because the security was, so it's a real trade-off, right? And they've said they think they lost a huge amount of sales because it was too complicated. The cart was 20 quid and everyone just bought it and that's their phone, didn't think twice, Anyway, so sign. Okay, we're building these boards. Unfortunately, I completely forgot to pack one when I came. Anyway, but we're using multiple ARM cores. And so, and this is an audio board. We do a lot of work in audio research and very specific. So it's got a heavily M7 DSP because we want to do DSP on one of the cores. The other one's a controller for handling MIDI and that sort of stuff. These examples. And so how do we want to program these? I want these boards, you know, if you think about, I put the audio board as our example, is because the use case, the users of this board, we're trying to build a digital instrument toolkit so you can build digital instruments and play around and experiment with them, are musicians. Okay? More and more, clearly we're seeing technical people, we're seeing non-computer science trained people become programmers one way or another. There's lots of great software, Max, MSP and other things. People are emerging that. A lot of web developers have come from more, you know, humanities subjects and things like that, which is great. I think it's a great contribution. There's no reason why they couldn't be brilliant at it too. However, again, if we spend months then fiddling around with JTAG and stuff and things and all that, it's not a very pleasant experience, and we can be pretty sure that not many of them will stick through the grind because they're trying to produce their next album or whatever, right? You know, and I suspect, we haven't done it yet, but even if we went to talk to companies like Ableton are a big audio company that makes software for computers for designing tracks and everything, and they're more recently starting to move into hardware, and we guess that it actually might be that they want to move some of their synth generation and stuff onto these bits of hardware. Even with their technical people, you stand up and say, oh, it's just all right low level, it's going to take you ages. They can put them off pretty quickly, okay? So I think thinking about the software stack is really important. ARM provide a really excellent low-level set of libraries called SimSys, which is across the Cortex series, and so it gives you access to the way that they have the blocks for the GPIOs and all that sort of stuff. It's all C-based. Some of it's obviously assembler because you've got to bring up the machine, and some bits, you know, you're bit banging and all that sort of stuff over that side. And then the ST, because we use ST, again, I'm not promoting ST in any way, is that they have a thing called STM32Cube. Anyone ever used that here? Yeah, everyone wished they'd never used it. Yeah, me. And it sits on top. I've got to be honest, it's a really shockingly awful piece of software, right? It's unbelievable. Like, you go in there, you can find a function to twiddle a pin, and it's 3 functions deep, and then none of them are inlined, and all you're doing on the ARM architecture is flicking 1 bit. I mean, that's you know, it's just unbearable, right? You know, you can't design software like that. But it's pretty easy to imagine how they got there. If you've ever worked in an embedded company, you know, someone writes something over here, someone wants to switch the arguments around because they're the wrong order, something like that. It's pretty easy to see how they get there. They've been taught at school not to use pound defines because it's bad, abstraction, whatever. It's easy to get there, right? And you can be sure, and I've done it, and I've actually seen it, that the performance is absolutely shocking, right? On chips that are only running at 16 megahertz, you know, and stuff, it's insane. Okay, and I suppose the code's been developed over a long period of time, that sort of stuff. Anyway, so says ARM, I've got to say, I suppose it's their business model. You know, they sell IP to other companies to build chips and everything. Their documentation is amazing. I'm not going to go on it. They have a whole set of libraries. There's, for example, really excellent optimized DSP libraries, you know, FFTs, all the convolution, all those things you'd expect for their architectures. A lot of it's, you know, written in assembler, or at least, you know, with built-ins and stuff, and they're bare metal, and they go all the way up to these more complex things which I haven't used, but handle all the debugging interfaces and all those sorts of stuff and things. And so it's really good, very well documented. Yeah, perfect. And it's portable between all ARM Cortexes, which for me, okay, we've made the choice to stick with ARM. Clearly that restricts some other architectures, we can use MIPS or whatever, but that's our thing. But we don't want to pick a particular processor or a particular manufacturer, you know, because at the end of the day, ARM is only an IP company. STM, which we do use a lot of, because they are cheap and they're good, provide these additional tools on top. But again, straight away, you're restricted to the STM, which is, of course, you know, what they would want. I can understand why they do that. But then tie that in with the fact that I find the tools aren't actually very good. They're really good to get Hello World going, really nice, they have initialization, but they're actually pretty poor once you get, that's just a personal thing, but that's what we found. Beyond that, which is a bit frustrating. And so, given that they're non-portable between ARM, Cortex-M, and the STMs, you know, and the code is not that really well optimized, I've found it that we've tried to move away from it. So, the conclusion so far, and this first bit of the talk, is that we'll use STM32 processors, we do, but mostly we're picking the Cortex-M processors. We're using SimSys because it is really nice, a very low level, well optimized, very well documented, and it spans all of the ARM architectures. We've decided not to use the Cube stuff because of its lack of portability, but also I just did find it difficult and to use and not very performant. The one really nice thing about the Cube is that if you start to put on external oscillators and everything onto your chips, which you might quite likely to do if you want to run them at high frequencies, you have to do with the STM. They'll do all the calculations for you and stuff and things, so to do the initialization of the clocks and stuff. So we always use that to generate it, and then I just put that back into our bit of code because it's a very handy tool. You don't have to sit down with a calculator and work it out yourself, which, to be honest, I'd probably get wrong if I did it. So I just let them do it, so it's great. So that is very convenient. And obviously it gives you all the pin layouts and all that sort of stuff, which is very useful. And we can't get away from using assembler because you do need it, which is actually quite fun when I'm teaching it to students who, don't even like C, so it's quite good. But it's actually tiny amounts of assembler. It's really great compared to what, you think in Linux was probably, half the amount of the Linux kernel, that you'd have to write now, and so that's quite nice. Clearly you could use C, right? C, I'm not going to put down C. C is a great language, and I use it all the time for lots of things. I use C++ as well. I'm quite a big fan of C++. I know there's lots of downsides of it, but whatever. But we could probably do better. Okay, and what I mean by that is that when we start to care about security and we start to care about the fact that we don't want our programs to crash because that might lead to being able to access the stack and those sorts of things, it's pretty difficult to verify C programs, right? If they're tiny bits of firmware, we probably can, but it's getting bigger and bigger, and that's getting harder and harder. And so I think that with a lot of other people entering this domain, we might be able to do better. And so we can apply the programming language, which haven't got that long. We could adopt C++ 17, absolutely. We could, I'm all for it, it's good. I think there's some really exemplar examples of this. The ARM's Mbed OS is an excellent example of a really well-engineered, structured design. It's not over-engineered, but it's been thought down. They've actually sat down and done some design before they've hacked on implementing it. And the University of Lancaster actually worked with the BBC and with Broadcom when they were developing the microbit and had this really nice, what they call device abstraction layer. It's kind of limited, but I do think it's a really nice example of what an API could look like. That's a good example. Of course, C++ suffers from all of C's shortcomings, null pointer dereferences, access of the 3, buffer overruns, things like that. And more of a, I do think this is quite important. Any of us who program with Python or JavaScript and things like that, and Node and stuff, will find that the lack of modern package and module system is quite frustrating. And of course, they're still arguing about it in the standards committee at C++ 17. Maybe one day we'll get there, but not yet. So, we're proposing Rust. This is just taken from the Wikipedia page, so you can read that in your own will. But the most important thing is that it describes itself as a safe and a practical language for system programming with a goal of being performance compatible with C++. Now, my experience is that it's not quite there yet, but it is pretty close. It's really annoying. You'll see from this standard, I don't know, it's a C-like language, it has a bunch of different things. I put Haskell up at the front there because it's taken a lot of its additions. It has this thing called traits, for example, which are effectively Haskell type classes. It has type inference. It has lambdas or closures, whatever you want to call them. And it's pretty modern. But what's really nice is that it is completely API compatible with C if you want it to be. Now, because it has things like overloading and all those sorts of things, it has to do mangling to handle that. But at any point, you can just drop out to C. So this is an extern bit, just like in C++, where you wrap the extern around it. You can have functions, and so you can link to it things. When you call a C function, though, you have to put it inside an unsafe block to say that you are willing to opt out of some of the more stricter things, i.e. you cannot get null pointers in Rust. You cannot get a free after free access or an access after free. You cannot do that. It uses a very strong type system to track basically who owns a pointer at any given time. That's a really nice feature. It does make programming in Rust quite tricky at times. There's no doubt about that, particularly if you're a beginner and you're not familiar with things like Haskell and stuff, but it's very powerful. So there are lots of benefits, safe pointers, compatible with C, some of the more modern, it doesn't have classes. Traits are a kind of merger between type classes and classes. Type inference has a lot more, but it has many of the modern features while still trying to achieve it. And it has a really great module system and package manager called Cargo. And there are a few constraints. It's a bit of a problem using it with embedded at the moment. It's LLVM based, and LLVM's great for its x86 target. Some of the other targets are still not as optimized as they could be, and we found some examples. So, for example, we had this single wire protocol with these cheap temperature sensors that came out of, many of you heard of D11, and it's just based on timing, a microsecond timing, and we found that LLVM was producing code that made us miss it, so it was very problematic. And so there was, it took me a long time to bloody debug that. Anyway, all right. There's lots of stuff that can be improved with Rust for embedded, but it is happening. There's quite a lot of work going on. These are crates, which are basically modules in a thing, and there are some exemplar examples for particular board support packages, effectively, but they're quite limited. That's the problem at the moment. So this is my last slide. The problem at the moment with Rust as for embedded architectures is, I think, that it's one of those open source problems, is that there's quite a few projects going on. They're often students, PhD students and stuff doing that, and once they leave, they kind of go, rusty and never get the plan and never get work on. And there does need to be something to step it up to take it over to the next thing. Mozilla, a huge investment in Rust, but they're really interested in the PC market because that's where their browsers run and everything and stuff, and so, and Apache and things like that. So I think that whilst it has huge potential for MCUs and embedded, there's still some time to go until it actually, I would recommend using it for real projects, like real in quote. We're using it, but then I'm at a university, we don't have quite the same deadlines and requirements to do that. We're expected to publish papers, and so Rust is quite a nice place to be working because, there's quite a lot of low-hanging fruit that you can grab and do stuff, particularly in embedded. Would I recommend it for doing your product that's got to be delivered next year? Probably not. Not unless you've hired a bunch of very, very smart Rust people, I think there's still a way to go, which is a shame because I do think it could offer a lot. But I've got to be honest, I don't think it's quite there yet. For embedded, I think potentially if you're doing concurrent programming on x86, then that'd be great. Well, that's my last slide, and I've got 5 minutes left, so perfect for any questions. Yeah?
In your time you invested in looking at Rust, have you also compared it to D and the state of the language D?
So that's a really good question. So before I looked at Rust, before I'd really heard about Rust, which was a couple of years ago now, I spent quite a bit of time with D, and I really like it, and I don't think Rust is necessarily any better. I got into a conversation with someone about Rust at a conference, and I just went that way, and so I wouldn't want to say, I haven't done any analysis to say whether the compilers are better or anything like that. I do like, for me, I've done quite a lot of work with LLVM. Before I joined the university, I was at AMD and did a lot of work with it, and so Rust kind of fits quite nicely for me, but just from I understand the tool chain already. I like that Rust has very similarities to Haskell, because my PhD was in Haskell and stuff, and so but I don't think that makes any argument that one is better than the other.
It's also more the question where the current state of development is between these two.
Right, exactly.
There is for D an implementation for CORTEX-M, but I don't know how the state is.
Yeah.
I've seen it some years ago.
Yeah, it's true. I haven't looked at that at all. So when I first got, I wasn't thinking about it. I just learnt it from a PC perspective and from the concurrent. But they both offer a lot for concurrency, so there is a lot of overlap. It'd be worth doing some work on it, but I haven't done it. Sorry to say. Yep.
I wasn't entirely clear when you were talking, but have you been using it as a teaching language? And so how are the students taking to it?
I've not been using Rust as a teaching language. I've got a couple of PhD students who are using it, one in particular who's doing the audio project, and he's taken to it quite well, although he felt, in the end, more comfortable learning Haskell first. He hadn't had any Haskell experience because so many of those ideas translate into, and he's a very confident C and C++ programmer. So I think he found it easier to learn some of those ideas in Haskell than to learn them in Rust, which I thought was an interesting insight. And I think that probably is the case. I think if you're coming from Haskell, you're familiar with C and C++, you'll pick it up really quickly. If not, it can be quite tricky. And my guess, my undergraduate students would find it quite hard. It's the borrowing, the kind of the pointer model that is pretty tricky, because all of a sudden you can't assign a variable in an if when you could before, because of the borrowing.
The way that C will kind of compile and break, whereas Rust makes you sort of upfront.
Right, yeah. So,
very frustrating.
which, yes, exactly, which is very much the Haskell way of doing things as well, right? They say that once you've got a Haskell program working, it's more than likely to, I mean, it's not really the case, but you know, it's a lot good chance. But that is problematic if you're not familiar with it and used to that kind of way of working, I think. Yeah. Yeah.
So one of the nice things about C for embedded is that it's like really easy for to do stuff like low-level register access.
Uh-huh.
You just put in an address and there you have it. How many hoops do you have to jump through with Rust just to do that kind of stuff, or is it really easy?
Well, that's an interesting question. So it really depends. I mean, obviously, if you could just go to an unsafe block, you can do whatever you like. You just in C anyway, so you could do that. And that's what quite a lot of people do with that very low-level stuff, and they just say it's trusted. There's been some work, yeah, up here, look, these guys at top, they've got this paper recently, just came out, where they were saying in the kernel, there's this thing called cell in Rust, which allows you to have and so they proposed a new type called, I think it's called type cell or something like that, which works around that. But that, and it's a software, it's purely implemented in software, but it, but you have to, it's a trusted thing. And what I mean by that is that you could, it breaks mutual exclusion, for example, and so people can have more. So, and that's the only way they've managed to get efficiency at the kernel level. So you could argue that that points to Rust actually their type system being broken. You know, it's too strict. But I think it's up for debate about how you want to look at it. You know, at some point you have to trust something. And so, but what we've done so far, I must admit, which is the register stuff, is just we go to unsafe for that and just trust it.
We're out of time for more questions.
Okay.